this tutorial, the 8-pin PIC12 F1572 will also be programmed to switch on an LED connected to pin 5 RA2, as was done for the previous assembly part of LED tutorial, this time using the C language with bare metal or register programming. Then the LED will be moved to pin 3 or RA4, and the required changes to the register bits will be modified, confirming how this is done to suit the change for pin 3 RA4. The PICKit4 and Snap can be used in any of the methods covered in the assembly part of tutorial, with the PICKit4 powering the device and circuit, or being externally supplied, or with the Snap programmer using an external supply. Then for another added part, the LED will also be toggled on and off, so we will need to use a delay function to achieve this. We will look at the PIC's internal clock sources, how to modify the default 500 kHz internal oscillator so that the oscillator runs at 16 MHz after a reset. During the C part tutorial, references to procedures used in the assembly part of tutorial are made, so if unsure, check the assembly part of tutorial for various procedures not covered here. The link to this tutorial is in the video's description below. Create a new microchip embedded standalone project. Use 1572 in the Select Device window, then select the PIC12 F1572. Then select the connected programmer. Finally, select your installed XC8 compiler and give the project a name, say PIC12 F1572_LED_bear. The PIC device configuration bits are found from the same menu used for the assembly tutorial, and when using the C compiler, uses a slightly different pragma format. Similar principle though. Only the field fosc option is modified to intosc once again. Generate source code, copy output text and paste into a new header file we create using a similar method as creating the assembly ASM file, but this time using the header file folder to create the new header file. Name the new header file device_config.h and paste the copied configuration bits output text into this new header file and save. So now we have a new header file with a device configuration code. We then need to create a new source file and name it main.c and save. Open the new source file by double-clicking the main.c file under the source files folder to open it in the editor's window on the right as seen here. The highlighted comments here are turned grey by the compiler and can be single line or block comments which are collapsible. These first few lines of code can include file name, author and basic description of the code section. To create a single line comment, use 2 / symbols and add comments after, which are ignored by the compiler. These single line comments may not span multiple lines. That is to say that each line needs 2 / symbols. To create multi-line comments, use the / symbol followed by the star symbol. Then add lines of comments. To end the multi-line comments, end with a star and / symbol. The multi-line comment is now collapsible and can be opened by clicking on the plus symbol to open all lines of comments. Next we use the #include directive to add 2 header files. The XCH header file allows code in the source file to access compiler-specific or device-specific features. Based on your selected device, the compiler sets macros that allow the XCH to vector to the correct device-specific header file. Do not include a device-specific header in your code or your code will not be portable. So the header file XCH consists of types, macros, and functions specific to your target device. It includes device-specific header files that also provide access to special function registers. The other header file, device_config_h, is the file we created with the device configuration code, which gets added to the main.c file during compilation. When we need to toggle the LED, we will use a delay function built into the Xe8 compiler. The #define _xstel_freq 16 MHz is used to indicate the system frequency in Hertz to the Xe8 compiler. Comment out line 17 by adding 2 forward slashes in front of the line of code until we get to the third part of this tutorial, when we will need to remove the forward slashes to include this line of code for compiling. The main function is next, beginning with the int main void, int for integer data type, main for the identifier, and void for the ANSI C keyword. A good reference for the meaning of int main void can be found at the link in the video's description below. Port initialization. We open the function with an open curly bracket, then use the special function register ANSIL-A and equal to hexadecimal 00 to set all bits of ANSIL-A to 0, which ensure the pin mode is set to digital in software code after a reset, suitable for this application. Remember from the assembly part of this tutorial, the default for pin mode after a reset is defaulted to analog mode. The C language clears the ANSIL-A register in one single line of code, simpler, but hides the process as seen in the assembly part of tutorial. From the PIC's datasheet, the example 11-1 for the initialization of port A is done in assembly, so if not familiar with assembly, this example would not be useful and the process not fully understood. Next, the special function register, or SFR, tris_A equals hexadecimal or 0x3b, sets RA2 as an output. The rest of the port A pins are set as inputs. Next, the special function lat_A equals hexadecimal 3b sets RA2 to 0, which will turn LED on for a syncing circuit. These two lines of code will be used when the LED is connected to pin 5 RA2. The lines of code below have the 2 forward slashes, turning them into comments, and therefore the compiler ignores. The lines of code are said to be commented out. And then jumps to line 44, which has the return 0, which successfully ends with a 0 result as defined by line 19 code with ANSI C keyword void, which requires a 0 result. This code will initialize the port pins and set RA2 bit low to turn on the LED. Once this has been tested, line 27 and 28 can be commented out as previously explained or deleted. Then remove the forward slashes from lines 30 and 31 so that the compiler uses these two lines for testing the LED on pin 3 or RA4. When moving the LED to pin 3 or RA4, the hexadecimal literal value will need to be changed from 3B to 2F, or 101111 binary for both lines. This sets the 5th bit of tris_A to digital output and sets the 5th bit of lat_A to 0, and so turning RA4 on when using the same syncing circuit as used in the assembly tutorial. With this modified code, the project can be built and loaded to PIC12 F1572, and with the LED now connected to pin 3 or RA4 will turn on the LED. Changing the value of these two registers, tris_A and lat_A, can be used for various combinations of pins required for digital output and status if on or off as required. But take note that pin 4 or RA3 is dedicated as an input only, due to the need for the MCLR or master clear being required during ICSP communication. This pin always needs to be available for receiving the signal as an input from a programmer for ICSP programming. Then pin 7 or RA0 and pin 6 or RA1 are required during programming and debugging for data and clock inputs, so these pin states cannot be monitored during debugging. They can be configured and function as required, just not monitored during debugging. We will now look at the third part of this tutorial for toggling the LED on and off using a built-in compiler function. Line 17 should have been commented out for the two previous parts of tutorial, but for this final part can now be uncommented, so that the XC8 compiler will now use 16 MHz for the system frequency when processing the delay function used in the next few lines. Line 37 can also be uncommented. OSCONbits.IRCF equals 0B1111 sets the internal oscillator frequency to 16 MHz. OSCON is the oscillator control register, and the 4 internal oscillator frequency selection bits indicated by the 4-bit IRCF field option, which are found from bit 3 to bit 6 of the OSCON control register. When set to 1111 is set for 16 MHz operation. Line 31 needs to be uncommented, so to allow the next few lines of code to toggle RA4 or the 5th bit on or off, else leaving this set will keep the LED on. The delay function can now be used, starting with a curly bracket, _delay_ms for milliseconds, and in brackets the value in milliseconds for delay. Then set RA4 equals to 0 to switch on the LED for the syncing circuit. The next line is the same, but setting RA4 equal to 1 switches LED off after a 500 millisecond delay. The return line of code completes and the code continues to run, flashing the LED for 500 millisecond intervals. Thanks for watching. The next tutorial will cover the same 3 parts with the LED in C using MPLAB MCC. Please leave a comment or suggestions to help improve the content.